so we are going to look at a situation where we're analyzing static equilibrium. So we have a problem, and we're going to use torque and force analysis to examine it. So let's imagine that we have a beam attached to a wall with a pin, and we are interested in this situation such that it can hold a crate hanging off of the wall, and that beam is also attached to a rope that extends to the wall. And let's imagine that suddenly the rope breaks. And it's such an old system that there's no records on what the strength of that rope even was. So you are being hired to figure out what rope to purchase in order for you to recreate this setup. And essentially, we don't want that rope to break, so it has to be of a certain strength. And how do we know what that strength needs to be? All right, so sort of a practical reason, so thing to think about. So we're interested essentially in the tension in that rope. And then of course we'll buy a rope that has a stronger breaking strength than that tension that's needed. Well, because the system isn't moving, we don't want the system to move. It's both in translational equilibrium, so the net force is equal to 0. There's no acceleration in any direction. And it's also in rotational equilibrium, which means the net torque is equal to 0. So all the torques exerted on this system are equal to 0. So if I'm interested in the tension, I know that tension is interacting with the beam. So my object of interest becomes the beam. All right. Now, I could analyze either the translational equilibrium or the rotational equilibrium, and in some cases I'm going to have to do both. We're going to find we do in this case as well. And as we practice, as we do more and more problems, we'll start to develop some strategies on which is the better approach to take first. Well, since I'm interested in the tension, it's going to be a force and something that could potentially exert a torque. I'm going to start with the torque analysis. I happen to know that that is the right analysis in this case, but if I started with the wrong analysis, I wouldn't have enough information, and I'd look for something that relates to the information I need, and I would just try that other analysis. So, if I want to do a torque analysis, I know I have to do an extended free body diagram. And I like to draw my object, which is the beam, in the orientation that it is in the picture when I do my free body diagram, and then the forces at where they're acting, of course. All right. I'm not going to put in the force tree, and I have very limited space in this particular environment, so we're going to talk about what those interactions are. Please, I encourage you to write down those force tree interactions so that you are practicing identifying those interactions very explicitly. Well, we know that gravity is interacting. The gravity is between the beam and the earth. And because this is a uniformly distributed beam, if I neglected to say that at the beginning, I apologize. This is a uniformly distributed beam. The force of gravity acts at the geometric center. So here's my force of gravity. Remember, that's mg. That's equal to the weight of the object. All right? I also have that crate on the end pulling down on the beam. So here's the force of the crate acting at the end of the beam. And of course I have the rope. It's pulling up and to the left. So that's a tension. Happens to be the thing I'm interested in. What is that tension? And then the beam is also interacting with the wall. Now, I'm not given the direction that the beam and the wall are interacting, but I know there's contact there. I know there's an interaction. And I also know that forces can be broken up into horizontal and vertical components. So I may not know the total force acting on that wall, but I do know that there's a piece of that force that's in the horizontal direction, and there's a piece of that force that's in the vertical direction. Now, how do I know it's to the right and up? Well, I'm making a guess, but it's a intelligent guess. The way to make that guess is to think about what would happen if the wall wasn't there. So if I suddenly removed the wall, what would the beam do? Well, it would slip down and it would swing in. If it slips down and swing in, that means something's holding it up and keeping it out. So my directions of the force the wall exerts, my horizontal and vertical components, they are a guess. And if I did it wrong, the physics is going to tell me eventually. But I think I've identified it accurately, thinking about what the object would do in the absence of that force. All right, so those are the 5 forces acting on the object and at the location they are. So then we're going to do a torque analysis. Every force has the ability to exert a torque depending on the axis about which we select that pivot point. So we have to identify a pivot point. Well, how am I going to identify that pivot point? Sometimes there's a natural indication. The object could rotate about a certain point that we see. But sometimes we want to identify that pivot point. We know it's not rotating at all. So we know the net force is 0. So let's identify a pivot point that allows it to be solvable. I don't know some of these forces. I know the force of gravity, it's given. I know the crate force, it's given. I don't know the tension, but I don't want to get rid of the T because I want to know the tension. That's what I'm solving for. And I don't know the force of the wall. If I don't know a force, I'm going to have a hard time actually calculating the torque by that force. But if I place my pivot point at this location, then those two forces don't exert a torque about that pivot point. And we'll find in the torque analysis that they're equal to 0, and I don't care what they are because I don't need them to do my analysis. So let's put the pivot point there, and then let's identify each of these forces and analyze the torques that each one is exerting. So, torque 1, torque 2, 3, 4, and 5, and I'm going to be able to sum those to give me the net torque, which remember is equal to 0. Torque 1 is the force of the wall horizontal times the radius of the wall times the sine of the angle for the wall. Torque 2 is the force of the wall vertical times the radius of the wall vertical, sorry, that should be H, and that should be H2, times the sine of the angle of the wall vertical. Force 3, that's my force of gravity, times the radius for the force of gravity, times the sine of the angle for the force of gravity. Force 4 is my crate, times the radius of the crate, times the sine of the angle for the crate. And force 5 is my tension, times the radius for the tension, times the sine of the angle for the tension. All right, so now we need to identify those radii and those angles on our free body diagram. So my radii for the force of the wall, well, based on the pivot point, that radius is 0. That's going to be awful nice. It's going to get rid of these two torques, which is what I was going for, because I don't know the forces anyway. All right, what about for the force of gravity? Well, this is the radius for the force of gravity. That radius is equal, whoops, I'm just rewriting my force of gravity. I'm going to write my radius, and that radius is equal to the length of the beam divided by 2. All right, what about the angle? Well, I extend that radius, and I curl to the force. So this is the angle that I am interested in for the force of gravity. That angle, so I'm just going to redraw the picture here. So here's my force of gravity. I know that this is 30 degrees. That makes this 30 degrees. Remember, that's my angle. And I know this to be 90 degrees. So the angle for my force of gravity is 120 degrees, and it's in the counterclockwise direction, so it's negative. All right, what about the crate? Well, the crate force has a radius, and it too has an angle. So extend the radius, curve to the force. The force of the crate, is it my force of the crate? The radius now is the length of that beam. I don't know what it is, but it's the length L. And similar to the force of gravity, it too has an angle of minus 120 degrees. Okay, and last, certainly not least, we have our tension. Well, my tension is at the same location as the crate. So we have tension times the length. Now, what is its angle? So I'm going to represent that because this gets a little bit messy. Of course, this is where we extend the radius and curl towards the tension. So there's my angle. And if I just redraw that to make the picture a little easier to see, this is the angle that we're interested in. We know, based on our picture, that this is at 50 degrees. That's given in the problem. We also know that this angle is 30 degrees, given in the problem, and so this angle is 30 degrees, alternate interior angles. 30 plus 50 is 80, and we know that this whole line is 180, so theta t must be 100. So I'm at 100 degrees, and I'm going in the counterclockwise direction, so it's positive. All right, so let's see where that leaves us. This gives us 0, and this gives us 0. I have the force of gravity, and I need to grab my calculator. Pause. Forgot to take that out. I apologize. So I have the force of gravity, which is given of the beam. So 1,200 times my length, which I don't know, divided by 2, times the sine of negative 120. And I get negative 520 times the length L. Should it be negative? Well, the force of gravity is trying to rotate this object in the counterclockwise direction, or excuse me, the clockwise direction, so we expect it to be negative. How about our second force, our second torque? Our force of the crate we are given as 1960 times L, don't know L, times the sine of minus 120. And that gives us negative 1697 times L. Okay? Again, I don't know L. And finally, we have the torque exerted by the tension. Well, I don't know the tension. I don't know L, but the sine of 100 is 0.98. Do I expect that value to be positive? Yeah, this is trying to rotate in a counterclockwise direction. So, I add these up. The sum of the forces are equal to 0. So I have 0 equals minus 520 times L, minus 1697 times L, plus T times L times 0.98. And the first thing I should notice is that L is in every term. I can pull it out and divide both sides by L. So I'm left with, I'm going to have to shift to the top, I'm left with 0 equals minus 520 minus 1697 plus T times 0.98. So once I divided both sides by L, 0 divided by L is still 0, and the L is eliminated from the right-hand side. So I add these two together, 520 plus 1697. I get 0 equals negative 2217 plus T times 0.98. And solving for T gives me a value of 2,262 newtons. So I need to have a rope that has a breaking strength larger than that. So my tension is 2,262 newtons. How did I determine that? Well, I recognized that this was in a state of static equilibrium, therefore the rotational equilibrium is equal to 0. If I do a rotational analysis, the net torque, determining the net torque equal to 0, I draw my extended free body diagram, I identify a pivot point, I selected that pivot point to eliminate some things I didn't know. These two torques were going to be awful hard to determine if I didn't know the forces that were exerting on them. Selecting the pivot point at that location tells me that they don't exert a torque about that pivot point. Identifying the radii and the angles, recognizing that I don't know the length, trusting that it's going to work out, but the force of gravity acts at the length over 2, and the rest of them act at the length L. And those angles based on extending that radii and curling to the force, recognizing that the angles could be positive or negative, and confirming that they give me the expected torque. It's always good to do that double checking. Adding them, summing the torques equal to 0 again because of that rotational equilibrium, and solving for my tension. Now I'm also interested in the force that the wall exerts. Unfortunately, I'm going to do that in a second video. I will give you the hint. The the computer kept crashing, so I had to keep restarting, and now I'm out of time. But I will give you a hint, and I would encourage you to try it if that video doesn't get posted before you want to analyze this problem. Now we need to do a force analysis. So, collapsing this into a single free body diagram and doing a force analysis that you're very practiced at will give you the force that we need. But we'll do that in a subsequent video. All right, good job.